Okay, good morning. So let's talk about stuff. For your written test number 2, I believe the performance should be overall better than written test 1. That's a good sign. I'm just had to do some final check on the result and the answers, so I can release the result by the end of this Friday, so you can take a look. As usual, if you want to talk about the answers or the test, come to my office hour, and then we can discuss it. And I will speak more about your exam, which has been scheduled already. That exam there is going to be in person, paper exam. You might be expected to write some code fragment, but not to the extent that you are required to for the programming test. I'll speak more about some tips for how you can prepare for the exam. Okay, I'll talk about it a little bit later. But for written test 2, definitely you can see the result and feedback by the end of Friday. And guys, it's really important now. That should be your first priority. In case you haven't started yet, may not be too late, right, for your assignment number 3. That one there is about basically a tree node and also about singly linked list node, right? This is what you were expected to learn from programming test number 1. That one is okay. However, when you combine that together with the tree node, that will pose a little bit of a new challenge for you. So you really have to struggle through the assignment number 3, and I'll give you guys some extra questions to practice. Your programming test 2 is going to happen in the final week on a Monday, right? Just don't forget, right? Everything is on schedule. And let me just give you some quick reminder about some resources that was given to you, just in case you haven't noticed that. And if you look at the assignment instruction, right? If you look at assignment number 3 instruction from E-class, well, it's due next Tuesday. All right, you really want to push yourself to really get started. At least you want to submit your best attempt. Okay, that will be beneficial to you, so that you wouldn't struggle that much for preparing for the programming test 2. All right, so resource number 1. You want to take a look at this section over here, the background. Okay, especially bullet point number 3. So this part over here summarizes about the trickiest bit about using generics. Especially now we got tree nodes, we got SLL node working together. So the generics working there will be a little bit more complicated than what you were experiencing in before the programming test, before the written test number 2. So you definitely want to take a look at this summary section there. I believe it's rather explicit and clear. You really want to go over that. Okay. And resource number 2. When you download the starter code, I'm just going to open that by some text editor. If you go into the tests package, and then you will see there is one class there. It's a bit small font size. I'll read it. It's called testgeneraltrees.java. It's one of the test classes given to you. That one there is not meant for you to implement. That one there is meant to show to you how we can build the link tree from scratch. This will be exactly the working environments you have to deal with for programming test 2. So I would suggest you may just want to start by looking at these 2 test cases, one on strings, the other one on integer, about how to use these 2 methods and to construct a tree. If you got any immediate trouble about this, you should really reach out to me or the TA. Having understood these 2 test cases will give you a very promising starting ground for finishing assignment number 3. Okay, assignment number 3 basically is about tree node, but as we learned pretty well, whenever you talk about tree, any methods you define on the tree, unavoidably is going to be recursive. So for sure, you have to know recursion pretty well. And we have done quite a bit of exercises so far. If you haven't really grasped the idea for recursion, you got another opportunity to really do it. Okay? That's about assignment number 3. If you got trouble, you really want to reach out. Don't wait until the programming test 2. That might be too late. Okay? And final announcement, for your written test 2 on Monday, for the missing time, we're going to have some makeup lecture for you. That one there is just going to continue with the recursion problem. I'll show to you. Again, that'll be the final announcement, and then we'll move on to other stuff. If you look at the lecture site, and then you will see, I just updated it earlier this morning. The good news is you have until the exam day to actually study that. This makeup lecture is not going to be covered in the programming test 2, so you don't need to rush. But that one there for sure is going to be covered in the actual final exam. Okay? And that one there will talk about 2 things. Number 1 is about the merge sort, and the other one is about a quick sort. They talk about conceptual idea, how you can sketch, so you can implement it in any programming language. Number 2, talk about how you can implement it in Java. If you look at the source code over here, it contains the complete implementation as well with JUnit test cases. Take advantage of that to really study that. And number 3, it talks about how you can trace the recursive call for both algorithms because they're recursive. Number 4, which I would say is the most important part you want to really make sure you go through, is about how you can solve the recurrence relation, which we spoke about for your binary search, which you studied for written test 2. I think since everybody has studied that, now you have warm up for the actual challenge. To really solve the recurrence relation for both the merge sort and quick sort is actually much more challenging than the binary search, because when you unfold the relation, you have to be more careful about counting the steps. Okay? You will see what I mean. So the video is very good quality, very informative. You just need to take time studying them and also digest. All right, so that's about what I want to say. Do you guys have any questions before I move on? All right, so we got this week, and then we got 2 more weeks. And I do have some plan to really finish off about a good amount of tree, and so you can actually graduate this course having lots of knowledge about trees. That's my intention. Okay. And by then, if you got any trouble, please reach out. That I cannot emphasize more. Okay, let's now take a look. I'll get to binary search tree. Hopefully we'll get to it, maybe in the second part today. But let's now deal with another important aspects about the tree. But before that, let's do something to warm up, which I promise I will do. Okay, this one will be some nice mathematical exercise we can do together. Right, so this, let me just recap very briefly, just spend 1 minute. What we covered last time was also very fundamental. If you recall, okay, sorry. If I just go to the lecture notes from last time. Okay, so last time we talked about binary tree, right? Different cases. And we talk about how you can define the left subtree and right subtree, right? Recursive notion. And also, we talk about how you can derive the sum of the geometrical sequence. So up to now, we learned about 2 formulas. One is for arithmetic sequence. The other one is for geometrical sequence, these 2. Okay? Well, if you really want some tips, I would say whenever you're counting the primitive steps in your algorithm, like what we did before your written test 1, most likely you're going to use the arithmetic sequence sum. On the other hand, if you want to calculate some property for your binary tree, most likely you have to use a geometrical sequence sum. I'm not saying always, but 99%. There could be some exception. You have to apply another one in the exam. You got to judge. All right, we talk about how you derive it. Of course, in case you forgot about the actual formula, you can always derive by yourself, hopefully within a few minutes, so you wouldn't waste too much time in the actual exam. And we talk about, this will be the most important page. We talk about how you can calculate the depth levels and maximum number of nodes in each level. And the way we do it is by using, again, that formula. Right? So make sure you really understand this page, so important. And based on that, we talk about complete binary tree versus full binary tree. And we talk about their minimum versus maximum nodes. Right? Make sure you review them. And we talk about the various 1, 2, 3, and 4 different sets of properties about bounding either the heights of the tree or bounding the number of nodes in the tree. And also number of internal nodes versus number of external nodes. Right? We'll talk about 4 different properties. You also make sure you review them. All right, so that's about what we covered last time. Okay? Pretty mathematical, but they are not too bad. What we're going to do today, just to begin with, let's do a little bit of mathematical analysis. Not too heavy, but I think it's fun. Okay, let me just go back to the slides and remind you about this definition. We talk about complete binary tree and full binary tree. There's another notion called proper binary tree. Okay, let's review the definition. A proper binary tree means each internal node has exactly 2 children. That means a node is either external with 0 children or has exactly 2. You cannot have a node which has only 1 child. That's what the definition says. And this will be one example. Let's check it. And then we're going to prove some property about proper binary tree using mathematical induction. All right, let's now take a look at this tree over here. For external nodes, no question, they have 0 child. For internal node, for example, this one here has 2 child nodes. For internal nodes over here, you have 2 child nodes. You don't have any internal node that has only 1 child. You don't. Okay, so that's what a proper binary tree is. If I just get rid of, for example, this branch over here, then this would not be a proper binary tree anymore because this internal node has only 1 child. Okay? It's important to know the definition. And let's now try to prove this property here, right? I'll do it together with you. So let's understand at least what a problem is, and then we'll do it by mathematical induction, which is pretty much fun. Okay? So let's say we are given a binary tree, and we assume the tree is not empty. We got at least 1 node. Okay? And then the tree is proper, according to the definition that we set over here. Simple definition. Having these 2 assumptions, we want to prove the following. The number of external nodes is equal to the number of internal nodes plus 1. That means we got more external nodes than internal nodes, and the difference is 1. Right, let me just remind you, whenever we say n with subscript e, the number of external nodes, and this will be the number of internal nodes. Before we do any proof, let's just convince ourselves this is indeed a valid property. On this tree over here, how many external nodes do we have? 1 here, 2, 3, 4, 5, and 6, right? How many internal nodes do we have? Here we got 1, 2, 3, 4, 5. So that means we got 5. And not surprising, 6 is equal to 5 plus 1. So the property does hold on this particular example. What we want to argue is this is going to be the case for any proper non-empty binary tree. How do we prove it? So the answer will be we're going to do mathematical induction on the size of this particular proper binary tree. We're going to do some base case with just 1 node. That's the base case. And then we have to state something called inductive hypothesis. And then we're going to argue if the tree has n nodes, what about we just extend the tree by the smallest amount? Would that extended tree still satisfy this property? That's what we're going to do. Right? That's mathematical induction. Base case is usually the easiest one. Why don't we start with that? So base case, there'll be only 1 node in the tree. All right? So I'm just going to draw the 1 nodes over here. 1 node tree. A quick question for you to check. Is this 1 node tree a proper binary tree? You have to check to see whether every internal node has exactly 2 children. But since we don't have any internal nodes, so it wouldn't violate the property, so that's okay. We have only 1 external node, in which case it has 0 child nodes, which is satisfied. Okay? So now in this case, you have to put down the number. Number of external nodes is equal to 1, right? Only this one here, the root. And the number of internal nodes is 0. All right? In that case, they satisfy this property, right? And in this case, we do have NE equals NI plus 1. It does satisfy. Check. So base case proved. Pretty straightforward. Okay? We only need 1 base case. And we're going to state inductive hypothesis. Inductive hypothesis. Okay? And that's exactly the property we are checking. Okay? For a tree, okay, how about this? For a proper binary tree with more than one nodes. It is the case. NE equals NI plus 1. Right? This is a very important hypothesis to write down first. And we may have to use it to argue later. This is something we assume, like axiom. Right? We're going to use it to prove something. Okay. Okay. That's good. Now we have to be a little bit more abstract. Oh, actually, you know what? Before that, I want you guys to consider this particular tree, which is proper, we have said before. Can you guys think about what would be the smallest extension you can introduce to grow this particular tree? Smallest extension. Well, let me, okay, I'll take Ferris first. Ferris, go ahead. By drawing 2 nodes, okay? But why not drawing just 1 node? Wouldn't that be even smaller extension? Wouldn't be proper anymore. All right, very good. So here you have many options. You can choose some external nodes over here, for example, and then you can extend it. You can turn that into an internal node by drawing a left child, for example, over here. But this itself is not sufficient because that means this new internal node has only 1 child. That would make the resulting tree not proper anymore. So the smallest extension you have to introduce is by introducing 2 nodes at the same time. We okay with this? It's a very important insight. So what I will do is I'm going to put over here and over here. So this will be the smallest extension. Of course, it doesn't need to be this particular external node. You can choose any one of them. I just chose one as one example. Okay? So this will be the smallest extension for a proper binary tree. And before I get down to a little bit more precise, right? One thing to note, inside. You can see the number of internal nodes and external nodes for this particular part doesn't change, right? External remains external, internal remains internal. So this part of the tree doesn't really matter. What really has to be careful for us is for this part over here. Because what used to be external has now become internal after the extension. And these 2 external nodes are also addition, right? So that's a critical insight you want to keep in mind using this example here. Okay? Any questions so far? If you're following so far, you're pretty much following it. Now we have to make it more general. Because to really prove about the inductive cases, you cannot just have a concrete tree. You cannot do that. You have to make it more general. All right, so this is what I would do. Given a proper binary tree, like that. Okay, just a binary tree, right? That's how we draw a general tree, the shape. Okay. Extend the tree by turning an external node into an internal node. That's basically what I just said over here. Okay? Let's now make it, and then I will, you know what? Let me make this diagram slightly smaller so I can show you. So let's say this one used to be external. Let's say simply choose this one here. Used to be external. Okay? And then I'm going to convert that into an internal over here and over here. So the number of nodes has been extended by 2. But how will the number of external versus internal nodes going to change? That's something we had to count very carefully. Okay? Okay, so now let's take a look. So let me just give you some notation. Okay? You can think about the NE and also NI. I'm also going to use NE prime and also NI prime. Okay, so what does prime really mean? Prime simply means the number of internal versus external nodes after the extension. Without the prime, that means before the extension, so we can compare them. Okay? So think about with the prime, it's after the extension. And without the prime, it's actually before the extension. Okay? It's a very common way to really annotate your variables, to say before and after the change. All right, guys, so here is something I'm going to ask you to think about. Okay? So here, I want you to know, after the extension, what is going to be n e prime? And what is going to be n I prime? Why don't we start with NE prime first? How many external nodes exactly? Mario, go ahead. It will increase by 1. I agree, but do you know exactly why it will increase by 1? Mm-hmm. Absolutely. Okay, guys, the final answer should be the number of external nodes after the update should be increased by 1. But how? Let me write down here, and then I'll explain. What Mario said was also exactly spot on. So it will be the number of external nodes before the updates. We're going to do -1 and also +2. Looks a bit silly, but there's a reason for that. Okay? For the -1 over here, that means what used to be external is not external anymore. So that's -1. The +2 over here means we are introducing 2. Right? So now it shows to you exactly how to calculate. All right? So that one is going to be the number of external nodes +1. The number of external nodes +1. Okay? That's number 1. And what about the number of internal nodes after the updates? Kathleen, you want to say? Oh, okay, that's okay. I thought you raised your hand. Okay. Anyone want to try? Internal might be easier to see. Yes, go ahead. Why? Yeah, in some way, yes. This one before the updates used to be external, but now that one there has been turned into internal. Yeah, +1. Absolutely. Straightforward. Very good. So that'll be the number of internal nodes +1. All right? All is good. Okay? And now we have to somehow relate this, and this together, and then we're done. Okay? And it's kind of obvious. Okay? So I'm going to put star over here, right? That will be the final arguments. By the inductive hypothesis, so here we got n e prime, which is NE +1, right? By definition. Sorry, by our calculation here. And we know that NE itself is NI +1. Right? And that one there, if you look at that, Ni +1 is exactly Ni prime. Right? So that one would be, sorry about the lacking of space, and then it will be Ni prime +1. So Ni +1 over here is exactly Ni prime. Okay? Right? That's how you figure. Okay, done. That's the proof. It's a very simple exercise over here. I would say it's nice to really do mathematical induction. It's always fun to do because you can see how something similar to recursion works. But I think the more valuable thing here is to see the recursive structure for a tree and how you can argue about its property in general. Okay. All right, guys, any question about this one here? Okay. All right, if you guys are feeling comfortable, let's move on a little bit, and then we'll definitely take a break in one moment. I would suggest we talk about some very brief application about binary tree, and then we're going to talk about some very important algorithm called traversal of the tree. That one shouldn't take more than 15 minutes, hopefully, and then we'll take a short break, and then we'll go on to binary search tree. How about that? Okay. Let's now move on with the slides. Okay. All right, so that's basically the proof we went over, and you guys can definitely take a look. Okay. Okay, application, binary tree. Okay, this one here is rather simple. It's just about kind of like a decision tree. For every condition, and you can say yes or no. And then if yes, something might happen. If no, something might happen. Decision tree. I think if you guys ever are gonna get involved in machine learning, decision tree is actually one of the training model that turns out to be very efficient. If you are interested, you can feel free to look up decision tree for machine learning. They actually got lots of nice stuff over there. But I think what we learned in this course about binary tree and later on binary search tree is going to build a foundation as well for decision tree. Okay, so I wouldn't dive too much into it. That'll be too much for this course. But if you're interested, Google decision tree and machine learning. You will see some nice example there. Okay, the second one is going to be more relevant to what you may have to do a little bit on the final assignments, right? Okay, I'll show you the tree directly. All right, so this is a typical way of representing, oh, sorry, you should be here. So this one here is a typical way of representing an infix notation. If you recall, when we talk about stack, we'll talk about how you can calculate postfix notation using a stack. So now we are going back to what you're familiar with, which is infix notation, okay? And for this one here, two things you have to know. Here, we only talk about how you can represent this particular binary tree. Using this binary tree to represent arithmetic expression. But to really, I'll give you some look-ahead exercise. Which we're going to go over anyway, but I'll just put it here. How to pretty print the tree by some traversal. And we're going to talk about traversal right after this. Okay, this is just look ahead. That's something we'll do. And what I want you to pay attention to is about internal nodes versus external nodes. If you look at external nodes, oh, sorry. This one here, this one here, this one here, right? External with no further child nodes. These are the leaves. So the way it works is for external nodes, they have numerical constants. On the other hand, if you look at the internal nodes, they represent binary numerical operations. You can see we got subtraction, division, addition, and multiplication, right? So here, if you look at the internal nodes, they are the binary numerical operators. Right, you can see here, for this minus, for example, that one there has one operand and right operand. Okay, you should really look at the subtree. So let's now take a look. So take a look at this one here. This is one subtree, right? And this one here is another subtree. Okay? So think about here, the left subtree, which is the left operand of the subtraction. And also this one here is the right subtree, which is the right operand of the subtraction. And the idea will just go recursively. Okay, I'll just hand wave a little bit. What about for this particular division? The left operand should be the left subtree. The right operand should be this right subtree. In order for you to either evaluate or to preprint, you will need to define some methods recursively. Okay, that's something you will need to do later. Okay. Are we okay with about representing this arithmetic expression using binary tree? Okay. Okay, so here, some question for you. If we got binary operators only, in that case, would it be always proper? Obviously the case. But what if we have some unary operator, for example, minus, right? For example, if I want to represent minus 3 plus 4, right? You can see this one here is a unary operator. In that way, the corresponding tree will not be proper anymore. Okay? For example, you can see here, I got plus still, and then I got 4 here, the right-hand side. What about this part over here? It's going to be some minus, and this is not subtraction, right? They're overloaded. It's simply just some negative sign. And then it will be, under that, it will be 3. Okay? That's another tree. That's binary tree, but it's not proper. Okay? That's a aside to actually clarify. All right, any question about this? All right, if no question, we're going to talk about something very important. And then hopefully 10 to 15 minutes, and then we'll take a break. Okay. Let's now talk about how we can do traversal. Okay, tree traversal algorithm definition, we're going to learn about 3. Okay, but they are rather similar. What's really a traversal? So if you try to do some traversal of a tree, you want to systematically visit all the nodes in the tree. You want to cover every nodes. But the way you do it, it has to follow a certain order. Okay? So we're going to learn about 3 different orderings. And traversal is not just for the tree. Later on, once you go to 3101, the algorithm course, you'll learn about how to do traversal on graphs. In that case, it will be done in a very similar way, but you have to use different data structure to really complete it. For this course, we'll do tree first to build a foundation. Okay, visiting each node may be associated with an action. So every time, well, for the purpose of exercise in class, we simply write out the nodes like a pretty printing. But in general, you can say, given this node I'm currently visiting, I can try to do some calculation, or I can try to do something else with it. That's completely up to you as a programmer. That's something you might have to do also in assignment number 4. You can print, you can determine some property, whether it's positive, whether it's matching some key, and that's so-called binary search on the binary search tree. That's something we'll talk about either today or on Monday. And you may want to maybe calculate the result of certain arithmetic expression. In that way, you have to say, I have the current value here in the root, and then what's the value in the left subtree? What's the value in the right subtree? And combine them together. Okay. All right, these are just some examples. Okay, let's now talk about the actual traversal. And I would suggest you guys maybe bring a piece of paper if you have one. For the first exercise, we'll do it together. For the second one, I'll let you spend a few minutes trying to draw the answer, and then I'll go over that. I think that'll be the best way for you to pick up these 3. Okay, let's go over some definition quickly. Definition is very easy to remember. Something called pre-order. And we got post-order. We got in order. So we got 3 different kinds. And it's important to remember, when we talk about pre-order and post-order, these 2 can be applicable, can be applied to a general tree, which means it doesn't matter how many child nodes you have for each internal node, doesn't matter. However, the last one here called in order traversal, that one only applies to binary tree. So you cannot do an in order traversal on a general tree where you have some internal nodes with more than 2 child nodes. Okay, that's the some precondition you have to remember. Okay, let's look at definition quickly. Pre-order means the following. Given n, a node, which might be the root of some subtree, you have to visit node n first. Okay, that's why it's called pre-order. You want to visit the root first. And then you're going to visit recursively each child from left to right. All right, that's a definition for pre-order. Pretty simple, but you're going to see how that works. The second one is called post-order. That one goes the opposite way. Rather than visiting the root first, we're going to visit its child nodes first. So you're going to see we put a loop over here at front. So we're going to recursively post-order traversal on the child nodes one by one. And then finally, we're going to visit this particular node. All right? So when you study for these three algorithms, you want to look at the definition, always remember. The definition themselves are pretty simple, but how to actually derive the resulting order, it takes some practice, which we're going to do. All right, why don't we do pre-order and post-order first? And in order will be pretty similar. Okay? Okay. Now, let's try. So for the pre-order, sorry. There we go. Yeah, let me write down the principle again, just to remind you. Pre-order is going to be parents and then children. And for the post-order, it's going to be children and then parents. All right? Now, let's go with the pre-order first. And let's think a little bit more recursively. When I say recursively, I meant think about subtrees. Okay? Now, let's say I want to do pre-order. Okay? What I want to do now is I want to have a pre-order traversal, let's say on the root of the tree, David. Now, to do that, the tree is way too big. It's not the base case just yet. Base case, in this case, will just be external nodes. Okay? If I just want to do pre-order traversal on this particular node, it's just the node itself. That's a base case. We're not there yet. Okay? So now, in order to do this, we're going to think about this guy here. And then we got a subtree over here. And then we got the subtree over here. I want you to know that structure first. Okay? What that will do is it's going to visit the parent first, right? Parents. So that one there, David, we can get it right away. And then we have to do a pre-order traversal child by child, subtree by subtree. Okay? In that case, the first one will be the pre-order for the left subtree. Pre-order of the subtree rooted at Ernesto. And the second one there, apparently is bigger, is going to be the pre-order of the subtree rooted at Chris. Okay, so here you can see Ernesto here, the root, and Chris over here, the root. Are we okay so far? And what will be the result for pre-order traversal on the subtree rooted at Ernesto? Just Ernesto is the base case because it's already external nodes. So you put Ernesto down. And then, if you want to do in pre-order traversal on this particular subtree, you got to do the same thing recursively. We have to think about this. So it's going to be Chris, the root. And then we have left subtree, right? And the right subtree. Okay, so it's going to be Chris, the parents, and then we're going to have, let me just move a little bit higher. Okay. And then we're going to get the pre-order traversal of the subtree rooted at Elsa, right? That's the first child. And then we also need the pre-order traversal on Anna. Okay, and let's now try to solve this one first, right? And this one here, right? Again, it's not a base case just yet. You have to visit the parents and then the child nodes one by one. All right. For the first one, let's be very complete. Okay. And how do we visit this? So we got alpha over here. We got tree here, and tree here. We got 3 child nodes. So you can see it's a general tree. It's not a binary tree, not necessarily. Okay. So that one there, we're going to put alpha. And then we're going to pre-order traversal on the first child, pre-order traversal second child, and pre-order traversal third child, right? And for pre-order traversal on the subtree rooted at Shirley, it's a base case. So we can simply write down Shirley. And here we can write down Vanessa. And here we can write down Peter. And then over here, what about the pre-order traversal of the tree rooted at Anna? Just Anna. And we're done. That's pre-order traversal. Okay? Now, let's see the result sequence. David, Ernesto, Chris, Elsa, Shirley, Vanessa, Peter, and Anna. Okay? David, the parents, and then Ernesto, and then Chris, and then Elsa, and then Shirley, and then Vanessa, and then Peter, and then Anna. That's the pre-order traversal. Okay? Of course, you definitely need practice on this, right? But that's the first one. Are we okay with this? Any repetition needed? You okay? Okay. Now, for the post-order traversal, it's going to follow something very similar, except that now we're going to do the child nodes should be, the subtree should be visited first before you can do the parents. All right? Can you guys give a try on the post-order? It's going to be very similar to the pre-order, except that, for example, here, if I am facing this one here, left subtree and right subtree, how am I supposed to proceed? Rather than putting David down right away, I should really do post-order traversal on this, and post-order traversal on this, and then David. Let me start with the first step together with you. Okay? And then let's see if you can figure out the answer. David here, first subtree, second subtree. Okay? So if I say the post-order of David. So post-order traversal is going to be the post-order. So here it's also PO, but it's really post-order. Okay? The post-order traversal of Ernesto. And then the next one is going to be the post-order traversal of Chris. And finally, we got the parents, David. Well, you can see just for the first step, David is here for pre-order, but David is here for post-order, right? You can see the order is different. Okay? Now, can you try to fill out what's over here? Okay? I'll give you guys a minute. Think about what should be there. Okay? Well, I think you should have no trouble about getting this one here, right? This one should just be Ernesto. That one's easy. Okay. But what about the post-order result from this particular subtree? What you want to compare is used to be this, but now what should that be? Okay. Anyone done already? You want to share your answer? Anybody? Post order. Okay to be wrong? Yes. Okay, one by one. Just give me the answer first. You first Elsa, you said? And then? And then? Okay, Elsa, Anna, and then? And then quiz. And then? And you're stuck. No? No, just tell me the final sequence. That's all I need. So here we don't really need to know the intermediate result. I want the final sequence. But I can tell you based on what you, maybe that's not what you meant to tell me. This one here up to now doesn't sound right. That's okay, don't worry. I appreciate it. You try, no problem. Number one, why would that be wrong? It's actually valuable for us to learn. When you say go Elsa, Anna, for example, Elsa, Anna over here, why is that wrong? Because the post order, we said the children should go first before the parents. You didn't even have Shirley, Vanessa, Peter, right? So how can the parents go first? So that's why it doesn't seem right. Okay? Okay, anybody would like to try? We can try one more, and then I'll give you the answer. Okay, go ahead. Just tell me the answer you have. Vanessa, we got it. Yes, good. Give me a moment. So Shirley, Vanessa, Peter, and then? Thank you. That looks right. Yeah, guys, I'll try to write a little more properly, right? Just lacking space. Okay, it should be, I think it should be okay. I'll say Shirley, and then Vanessa, and then Peter, and then Elsa, and then Anna, and then Chris. Okay? And I'll make a little bit more annotation for you. And for that one there, you can see Shirley, Vanessa, and Peter, this will be on just the child nodes over here, right? One by one. And then you got the Elsa over here. And then you have Anna over here. So that's the traversal for the next child nodes. And then you get to the quiz over here. All right, you just want to see exactly the order. Okay? Are we good? Okay. Why don't we take a very short break? But for those of you who want to try right away, I'm going to leave the page over here. Think about what's going to be pre-order traversal on this and post-order on this. Okay? But meanwhile, we can take a break for sure, if you want to try. But I'm going to go over the answer with you after the break. Okay, you can get your device. I'll turn back to that page in a moment. If you can get your device, let's take attendance. Okay, you can check in now. Yeah, we're taking attendance now in case you don't know. Yeah, so please do it. And then I'm going to close it pretty soon. All right, can I close it? Good. Thank you. And let's take a 2-minute break. But for those of you who really want to try, you can take a look at this and see what should be the pre-order versus post-order. You can think. Otherwise, take a break. I'll leave the option to you. 2 minutes. Actually, you know what? I'll talk about it. Yeah. Just tell me what's the 3D printing result. Mm-hmm. Okay. Oh, sorry, over here. The same tree. Doesn't work for you?
I got to do the attendance, but it clicked, but the poll ended the second I clicked into attendance.
Okay, why don't you sign anyway? So just in case, yeah.
Okay, I just want to make sure because I got the attendance, but I missed it.
Of course, just sign anyway, yeah.
I'm right here. Thank you.
Thank you. Yeah, please, yeah.
You.
Can you please put March 22nd here for me? Yeah. Thank you. Awesome.
Thank you.
Thank you. Okay, guys, we'll take 1 more minute, and then after the break, I'll give you another 1 minute to really do the exercise, right? But for now, you're not required to. Okay. Okay, we'll start in just 1 moment. Okay, let's start again. And I'll suggest I give you guys 1 more minute. For those of you who didn't get a chance to try, I'll suggest try at least one. Okay, on the tree here, do either pre-order or post-order traversal. Okay, take 1 minute, and then we'll go over the answer. Okay. Okay, just 1 more moment, and then we'll go over the answer. And then, of course, if any volunteer would like to contribute, I'll be happy to take it. Alrighty. Okay. Why don't we start with the pre-order? Anybody would like to volunteer your answer? Anybody? Okay, if no, I will just tell you the answer. Okay? Start with this, and then parents, and then this, 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 and then the plus, and then the minus, and then the 9, and then the 5, and then the 2. Okay? And then the plus, and then multiply, and then 3, then minus 7, 4, and then 6. Thank you. Well, hopefully if I give you something similar in the exam, please just get it right. Okay? That'll be my bonus for you in the exam to give you some question like this. Please get it right. Okay? And the only thing I want to bother you further before I go to the post order is if you look at the minus over here, right? This guy here. And then from the divide all the way to the 2 over here, right? That's the post order of the divide. And if you want to do subdivision to really analyze, I'll let you do it. Okay? And then finally, this part over here is the result from the post order on the plus. Okay? Pre-order. One thing you definitely want to avoid, maybe I think that's my impression, maybe from the beginner, not really you guys, but maybe from my students in the earlier years. When you do pre-order, let's say you start with this, and then you do this, all good. You don't want to jump right away to plus over here. You have to finish the traversal for the entire subtree here before you can move there. Right? That's a very important guidance. Okay? All right, post order. Anybody before I got to do it again? Okay, how about do Ferris this time? Okay, just tell me the answer first. 3, 1. Okay, 3, 1 plus 3 multiplication. 9, 5 minus 2 plus division. And then we have 3, 7, 4 minus multiplication, 6 plus, and then negative. Let's take a look. Okay. 3, 1 plus, 3, 1 plus, 3, and then multiplication, very promising, 9, 5, minus, and then 2, and then plus, and then divide, pretty good. And then 3, 7, 3, and then 7, 4, right? 7, 4. And then you get to the minus over here, and then you get to the parents. And then you get to multiplication, the parents over here. And you get to 6 over here, you get to plus, and then minus. Plus, and then minus. Awesome. Right, guys? If you're still having trouble or struggle with finding this, reach out. All right? You still have time to get used to it. If you ask me, that will be the absolute basics you will need to know. Okay? But you still have time to grasp. Yes, question?
So for the post order, when we're going from child to parent,
Yes.
whenever we reach a parent that's on the same level of another child, we move over? Is that what's happening?
Okay, so thinking this way. Okay, let's do a little bit more hand waving here. Let's say I want to do post order on this, right? So my first encounter will be the root over here, the left subtree, and the right subtree. Okay? So I can never get to this until I have done with this and done with this. That's why you see the minus is actually over here. Okay? Let me make some annotation right away. This is the root, and then all the way to division here, and also over here. Right? You want to think about this part here is a post-order traversal result of this tree. And this part over here is for this subtree. And we got a minus. Okay? And then let's say you're handling this. Again, you're going to have, let's say, divide, which is over here. We'll go last. And then you got a post-order traversal for this, which would be over here. And then the post-order for this, which will be over here. Right? You just kind of keep going. Does that kind of answer your question? Maybe? Okay. Yeah. All right, guys, one more. And that one should be very straightforward. And then I'll tell you the answer right away. The in-order traversal is only for the binary tree. And this one tells you, okay, I don't want to go for extreme. Like, let's say I'm going to either go for the child before the parents, or go for the parents before the child. I want to go for the left child, left subtree, and then the parents, and then the right subtree. A little bit more balanced. Okay? So the principle is over here. And why don't we do it together? Okay? For this one. And then you can definitely practice. This one, arguably, is actually going to give you something that's closer to your understanding about arithmetic expression. Okay? And by the way, I have some little mental exercise for you. When you do post-order traversal, the output is going to give you something we have seen before. Postfix notation, when we talk about stack. Okay? Look it up and try to draw some connection. Okay? Okay, take a look. They're connected. All right, for in-order traversal. Okay? How about I write down the answer directly, and then we'll do a little bit analysis. Okay? Okay, so child nodes first. 3 plus 1 multiply by 3. Divide 9 minus 5 plus 2. Okay, and then minus, right? You can see I go for the parents over here before I go for the right subtree, right? And then 3 multiply 7 minus 4. And then plus 6. Okay, over here. All right. And now for this one here, let's do a little bit more analysis here. Okay, so here you can see the minus is in the middle. Okay, and then if you look at the left subtree over here, okay, that's this guy here, where the division is in the middle. And then if you look at the right subtree over here, of course it is here, here. And then you can see the plus is the operator over here. Okay, that's in order. Okay. Should you know all? Yes. All right. But we did pretty closely about how you're supposed to figure them out. Okay. Another way for you to practice more, you can maybe take this input tree and try to expand it or make it a little bit different shape and try to look at the pre-order, post-order, and maybe in order if that's still binary. And if you want me to check your answer, just drop by and then we can take a look together. Okay? As I said, these traversals are really considered as basic for the exam. So just get them right in case I put a question on that. Just want to get the marks. Okay? All right, so that's about everything I want to say about general tree. Okay, so that'll be part A for the tree series lecture. We got another 2 parts. I know we got a little bit time today, about 10 minutes or less than that. I can do a little bit today. And then we got 3 more classes. We'll see how that goes, right? I really want to give you guys as much as I can before you have to graduate from this course. We'll see. All right, let's take a look. And pre-order, post-order, and this is more like a textbook example, just show to you. If you got the table of contents from the book, that's how you actually traverse. The same idea, right? I'll let you take a look in order. Okay, that's it. And then without a break, let's just go for another less than 10 minutes, and then we'll finish in time. Okay? So this will be part B of the tree series lecture. And we're going to do binary search tree. So this one here is not too bad. I would say the beginning part is more important, which is about the search property. Let's see how much we can go over today, and we'll continue on Monday. Binary search tree. So the learning outcomes will be, we have to understand what a binary search tree is. In summary, it's basically binary trees, which we learned already, plus something called search property. That's what we're going to learn, maybe today, a bit. And then how we can implement a generic binary search tree in Java. Good news, the generic binary search tree that we talk about in class is only going to be in class. I might ask you some specific question, maybe on the exam, about binary search tree. That's possible. However, for your programming test number 2, you don't have to worry about this particular implementation. Okay? For your programming test 2, as I said, only worry about your assignment number 3. Okay? If you can really complete your assignment number 3, go over the solution later, reach out for help, it should be fine. Right? I wouldn't give you something that's more difficult than your actual assignment. Okay. But this particular generic implementation is still worth your time to really study that. It's actually very useful, even beyond this course. And we can learn about, given that the tree is a binary search tree, how are we supposed to do insertion, searching, and deletion? Okay? You might be saying, oh, why is it so difficult? If I want to remove a node from the tree, I can remove maybe the rightmost node or remove somewhere. That's not true. Because whenever you do some removal, you want to make sure the tree from the deletion still maintain its search property. That's something we need to talk about. It's not as simple as you might think. All right, so I would say let's only go for less than 5 minutes, just for you to have some idea about the binary search tree. The binary search tree, let's look at a recursive definition. Before that, I'll go over this slide here maybe on Monday. But let's now take a look at one example. Okay, just this page. I want you guys to look at this tree over here. Stare at this tree for just one moment without me even telling you what a binary search tree is. Why don't you guys try to see, from this tree, can you see any pattern over there? I'll give you some visual hints over here, if I may. When you look at this tree here, look at the values of this guy here, and left subtree and right subtree. And you want to look at that for recursively, right? You're going to look at, for example, for this subtree here, also look at the root, left subtree, and right subtree, okay? Without me even telling you. You guys are intelligent enough to figure out before I tell you the definition. Okay. Now, give everybody a chance to really look at that, right? And then I'll talk about it. Okay, maybe one more moment, and then to see. So this is a very typical binary search tree. And one possible exam question could be, I give you a tree that looks like this, and then I simply ask you, is it a binary search tree? If it is, justify it. If it is not, tell me where it goes wrong. Before you guys tell me the answer, okay, or any insight you can see, I can easily make this not a binary search tree anymore. For example, let's say I change this guy over here from 82 into 7. If I change this one here, it's not a binary search tree anymore. And if you don't know the reason, that's okay, but that's something you were supposed to know when you write the exam. Okay, now, what's your guys' observation? I'll take some insights, and then I'll tell you the answer, and then we're done. Yeah, that's pretty good observation. Okay, guys, here's the answer. Given the root, since it's a binary tree, look at all the values on the left subtree. All of them are strictly smaller than the root. For example, 17, 8, 32, 28, 21, 29. They're all smaller than this. Agree? Symmetrically, all the values on the right subtree, you can see 88, 65, whatever, they're all strictly greater than this. And this notion here is not just for the root, it's recursive. Now, this subtree here is also a binary search tree because this is the root. The left subtree, every node, well, in this case, just one node, the value is strictly smaller than that. And if you look at the right subtree over here, all the nodes over here, the value are strictly larger than this. Yes? Yes, yes. That's a very good question. Let me address this right away, and then it may not make 100% sense until next time, okay? The question was, for example, let's say if I have rather than 28, for example, let's make it 32. Okay, that's what you meant, right? If that's less than or equal to. The answer is it's going to make the searching process ambiguous. Typically, the values you are going to use for the binary search tree will be the key values for searching purpose, which we'll talk about next time. And the keys for searching should be unique. So now, if you have two keys of the same value, in that case, if I say I want to search in the tree with maybe key 32, I wouldn't actually know whether I should return this one or this one. Mm-hmm. And also that it's also going to compromise the running time. Anyway, so we'll address a little bit more. It's a very good question. So I will make sure I revisit this maybe next time. All right, guys, any question? So today, pretty light, just want you to get some intuition. Yes, question? Very good question. Okay. I'll also address that next time, but let me tell you the answer right away. For binary search tree, also the particular implementation we're going to study, internal nodes, only internal nodes will study the key value, will store the key value. The square ones are external nodes, which does not store anything. And this particular implementation is going to make the searching, insertion, and deletion easier to write in Java code. That's something we'll address next time. Oh, it's okay. So whenever you want to do, for example, any kind of traversal of the node, you will always ignore the external nodes. You only count for internal nodes. That's something I'll address maybe on Monday. Mario, quick question. It's actually possible to So binary search tree actually got many applications. So if you look up the Java API, if you're interested, there's something called tree map class. That one there is to really implement a hash table API using a binary search tree. Or to be more precise, maybe balanced binary search tree. So that one is a little bit more advanced for this course, but I would say, yes, right, short answer. You can use a binary search tree to really implement some map. Yes, you can do that. Guys, thank you so much. And then I can emphasize more, please do your assignment number 3. That's going to lead you a long way for programming test 2. If you got any trouble, reach out. Okay, take care. Bye-bye.